Right, in this video I'm going to go over 3 questions on refraction of light. 3 questions. So starting with the first question, use the values of the refractive index in the table. The table has been given to find the angle of refraction in glass. If the angle of incidence in A is 46 degrees. So given that the refractive index of glass is 1.5, so we can work out using the formula sine I over sine R is equal to n. Sine I over sine R is equal to n. Right, so we are given n is 1.5. Sine I will be sine 46, and then sine R is our unknown. So we can make sine R the subject of the formula. It becomes sine 46 over 1.5, giving us 0.60. Now, finding the sine inverse of that, or arcsine, it will be 28.7 degrees. 28.7 degrees. Second question, that's B. The speed of light in water. If the speed of light in air is 3 times 10 to the power of 8, speed of light in water. Now there's a formula which goes by n is equal to the speed of light in air over the speed of light in the medium. Now if we let the speed of light in the medium be x, we then have 1.33, that's the refractive index of water, is equal to 3 times 10 to the power of 8 divided by x. Now making x the subject, it comes to be 2.26 times 10 to the power of 8. Then moving on to the next part C, find the refractive index of a liquid if the angle of incidence in air is 30 degrees and the angle of refraction is 19 degrees. 19 degrees. Right, so again, here n is equal to sine I over sine R. So we are given I is 30 and R is 19. So sine 30 over sine 19 should give you 1.54 as the refractive index. Then lastly, D says find the angle of refraction in diamond if the angle of incidence is 30 degrees. So we're using the same formula, n is equal to sine I over sine R, and in this case we're given I, we are not given R, so sine 34 over 2.4 giving us 0.232997, and finding the sine inverse of that gives you 13.5 degrees. 13.5 degrees. Now moving on to the second question. So here we have recorded them as odd numbers. Complete the following diagrams to show why a fish in water appears shallower than it really is when viewed from the side. Now the light rays, one thing I need to say that the light rays have to come from the object and then get refracted to the eye. That is to the actual object. So this is the real depth, and the apparent depth will be that which is drawn in broken line. Right. So our eyes get deceived because they cannot refract light on the boundary. They cannot refract light on the boundary shown there. So the light rays move in a straight line from the apparent image to our eyes. So the broken line there are the imaginary rays that are going to the eye, whereas real rays are being refracted at the boundary to the eye. So this is how you draw. Make sure that you always draw arrows to show rays. Very important. Then lastly, number 5. Number 5 says copy and complete the paths of the rays through the glass prisms. So first of all, you've got this glass prism which is made of an equilateral triangle, so 60 degrees on each corner, and then we've got one which is 45 degree and 90 degrees. Right, so I think I worked this one out again. So it's going to be like that. For the first one, right, what you need to do is to establish. Now, since the ray is entering at an angle of incidence of 0, that is in the line of the normal, there is no refraction. So when it hits the other side of the prism, then it gets refracted. But before you find out how it's going to get refracted, whether it's going to undergo total internal reflection, you need to draw the normal. So you draw the normal to that surface, and that normal to the surface should give you a clue whether this is going to undergo total internal reflection or not. Now in my case, I found out that the angle, it is going to form an angle of 30 degrees with the side. Now the angle of incidence is 60 degrees, and we know the refractive index of glass is the critical angle of glass is 40 to 41.8 degrees. So this angle of incidence is greater than the critical angle, therefore it's going to suffer total internal reflection. So it's going to go the angle of incidence equal to the angle of reflection. Then it goes down. Now as it goes down, it goes again 90 degrees to the surface with which it's going to emerge. Then it's going to go out unrefracted. Then for the second prism, this is a 45 degree prism. The angle of incidence again is 0, so it passes through unrefracted until it reaches one of the sides and then get refracted. Now we're going to get 45 degree angles. Again, we said the critical angle for glass is 41.8 degrees. So this 45 is greater than the 41.8. Therefore, total internal reflection will occur, and it's going to go parallel to the other side, through which it entered. Then, when it reaches again the third side, it's going to be totally internally reflected because the angle of incidence is greater than the critical angle, the 45 degree angle, therefore giving a total internal reflection. Then part B says, why is there no refraction when the ray of light enters the prism? So I've already answered this one. When it enters at an angle which is 0 degrees, angle of incidence of 0 degrees, there is no refraction that occurs, that is through the line of the normal. And then lastly, name two instruments that use prisms to reflect light. With the binoculars, and also we have the periscopes. So these instruments, they use prisms. So I think that's it on the questions. Please let me know in the comments below if you have any questions on refraction, so that I will be happy to answer all of them. Signing out.